Welcome to the Chapter 12 Study Guide. For obvious reasons, I'm starting your study guide on question number 4. I'm not exactly sure why this picture is here already, but we're going to run with it. So it says, examine each of the statements. If they're false, explain why. The first one is, the activation energy of a reaction depends on the overall energy change of the reaction. And that's false. If we take a look at this graph, we have reactants and products. Our activation energy is measured from reactants to products. Versus enthalpy, which doesn't care about the path whatsoever. In this case, it was an endothermic reaction. If we look at an exothermic reaction, again, activation energy is measured from reactants to products, and we don't care about the change in enthalpy, which in this case, it is exothermic. The next one asks about rate law and coefficients, and no, never, not at all. Not going to happen. Well, except for the elementary steps in a reaction mechanism, yeah. Otherwise, no. The answer is no. Most reactions occur by one-step mechanisms. Nope. Probability does not favor that process. Think about the puzzle. Yeah. Throw all those pieces up. Think they're going to land? No. Not in order, they're not. You're not going to get that puzzle nicely made by pitching them up in the air. Same thing, reactions do not occur by one-step mechanisms. In fact, just to be on the clear side, I'm going to take my handy pen, which isn't working, but at some point I would have drawn a big ol' X. No, it does not. This question's asking you to determine the rate law using the initial rates method. Now, this relative rate that's here, is really rather unnecessary to solving this problem. This is a relative rate, how one thing compares to another. It doesn't have anything to do really with the overall rate law. For the second problem, again, I must have had a serious typo problem when I typed your study guide, for which I apologize. Well, we're going to use this one and we're going to use this one. And since we already changed the I's, but it doesn't matter. I'll try to say that again. It doesn't matter because these two are going to drop out anyway. We have our generic rate law equals negative K. We already know the iodine ion is to the 1. And it's this one, the second reactant, for which we are trying to solve. And remember I said a minute ago that we were seriously trying to figure out why I can't type? Well, let me tell you, the second reason I can't type is this reactant right here. Notice these two are the same, and they should not have been the same. So this one is really 3.125 times 10 to the negative 8th. All right, with that in mind, I'm going to go ahead and write down the rate of the first one. And I don't care about the K's and I don't care about the I's because I know they're going to drop out. So I'm going to skip on to the next step. And 0.04 raised to the B. Divide this one by 3.125 times 10 to the negative 8th. 0.01 raised to the B. That's going to give us 4 equals 4 to the B. So B in this case is also 1. The last part of this problem asks us to solve for K with the first experiment. Ideally, to solve for K, you should solve for K for each of the experiments and then find the average. But, clearly on a test, I'm not going to ask you to do that. I am going to change this one to reflect what it should have been. Okay, so now that we've done that, let's go ahead and solve this problem. We know that the rate law is rate equals negative K times the concentration of I, which we already know is to the first order, and the concentration of the second reactant, which is also to the first order. I'm going to go ahead and rearrange for K. Now I'm going to substitute my values in from the first experiment. and get out the handy dandy calculator. So our rate constant for this particular experiment, the value is 3.9 times 10 to the negative fourth. However, there's still this negative sign on k. So our slope, which is negative, so that makes sense, is negative 3.9 times 10 to the negative fourth. And now we just need to figure out our units. And to figure out the units, I really like to just sort of rearrange this step. And we have rate, which is molarity per second. We're going to divide that by molarity squared. And another way that you could rewrite this is I could write molarity per second times, now remember when you divide fractions you have to flip, correct? Or, well, another easier way, actually an easier way for you to look at this might be, instead of looking at this mess, we can exchange this one for, I'm going to do this over here, m over s. Let's erase so I don't get you even more confused than I might have already. Let's erase this one. We're going to erase all this. All right. And then I'll change my pen color for you. Okay, so start off with how this guy looks. And that is molarity per second divided by molarity squared. And an easier way to write this is to recall that this is the same thing as molarity per second times, now what's that going to be equal on the other side? Well, we could say that this guy is equal to molarities per second divided by molarity squared. So when you divide fractions, you have to flip the second. So that's 1 over m squared. That one drops out. That drops out. So our units end up being m to the negative 1, s to the negative 1. And whew, we're finally done with that problem. Okay, I'll give you a minute to read through this problem if you haven't already. The 2 points I chose for graphing, which are going to be kind of hard to see on the PowerPoint, but they're a lot easier to see on your paper. I chose this point. So if an ordered pair is x comma y, that first point is, let's see, our x value then was 10 comma negative 2.6. And then the second point I chose was, okay, good. I just want to make sure I wrote down the right thing. And the second point I chose was this one, and that gave us, let's see, x is 15 comma negative 3.15. So the slope then, rise over run, I know you guys are good at saying that, but it's the change in x's over the change in y's. So the slope, which remember, that's our k value. I can use my pen. So the slope then becomes, let's see, we have negative 2.16 minus negative 3.15 divided by 10 minus 15. I'll go ahead and calculate this out. So I end up with a slope of negative 0.198. Now I'm ready to finally solve this problem. Well, let's see, we needed ln of the natural log of a, that's what we're solving for, equals negative kt plus the natural log of a sub 0. And we already solved this a second ago. And we end up with the natural log of the concentration of A is going to equal negative 0.198. And we're looking at time 30 seconds plus, let's see if I can find where I wrote that other number down, plus a 0.20. Okay, ln of A then is going to equal negative 5.74. Raising both of these guys to the e, A gives us a concentration of 0.0032 molarity, which makes sense. If you continue to draw this line down to 30 seconds, your concentration is seriously going to drop. You have a -5 here, and look at that. Yeah, it's going to keep dropping, so that number makes sense on the graph. That number makes sense in reality. We are done with. The key to solving this problem is to notice that each successive half-life, in this case, doubles. So, like this graph, when each half-life doubles, you are dealing with a second-order reaction. So the first thing we're going to need to do is use this equation up here to solve for K. So I'm going to rearrange this equation for K, and so that K is equal 1 over the first half-life multiplied by the original concentration. And when I plug everything in, we get a K value of 1. And I know I should put units on here, so let's see, that's inverse minutes and molarity to the -1. There we go. Now that you know that, we can use the integrated rate law for a second order reaction. 1 over the concentration of A is going to equal KT plus 1 over the original concentration. And this is the one we're solving for. 1 over the original concentration then is equal to 1 multiplied by 80 plus 1 over 0.1. And then we end up with 1 over the concentration of A is going to equal 90 plus, sorry, that should be an 80, I'm getting ahead of myself, plus 10. So then we have, bringing this up here, 1 over the concentration of A equals 90. So the concentration of A at time 80 minutes then is going to be equal to 0.011. That's it. This is a proposed reaction mechanism below here. And remember, for a proposed reaction, for reaction mechanisms, we can use the elementary steps to write a proposed rate law. And the elementary step has to agree with the slow step. So our current rate law for this reaction should be the rate is going to be equal to -K times the concentration of C4H9Br to the first power, because this is the only time you can use coefficients. Now we need to write an overall balanced equation. Well, that simply means just add them up in this case. So I don't see any more of this guy around here. So we have C4H9Br, and now I'm going to look for this one somewhere, C4H9. There it is. So that's one of our intermediates. So we don't need that one anymore. Is there water anywhere? Yep, right there, but they're both on the reactant side, so we have 2 waters. And this guy right here is here, so that's another one of our intermediates, C4H9OH plus, so we can ignore these guys. And we've already used these two, and that one. All right, bromine, going to have that, or should I say bromide, plus C4H9OH plus hydronium. That's it. This problem asks if you understand how to read the graphs. So first we have to put reactants and products on here. Right, reactants I'm just going to label with an R, products then with a P. Activation energy for the overall reaction. So if I could draw a straight line, I would. I'll do my best. There we go. And that's where the activation energy would be for the overall reaction. You want to go with the bigger one. So here we have E sub A. And the overall enthalpy is simply the difference between the reactants and the products. So there is how we measure delta H. Transition states here and here. These are your transition states or activated complexes. Either one is fine. The intermediate is right here. And the rate determining step, that's this point right here. That is your rate determining step. Or is it this one? What do you think? It's this one. And the reason it's that one is because if it takes more energy, that means it's the slower step. And the slow step is the rate determining step. This is a problem you should pay particular attention to. While you do not have to memorize this equation, you will have to use it. To calculate the energy, the activation energy, we're going to use the equation of the natural log of K2 over K1, and that's going to equal the activation energy over R times 1 over T2 minus 1 over T1. Make sure temperatures are in Kelvin. Huge, huge important step. Kelvin. Okay, so a second order reaction has rate constants of this amount, so the natural log of 8.9 times 10 to the negative third, and then we need the second one, 7.1 times 10 to the negative second. We're solving for the activation energy, and we know this is in kilojoules and R is in joules. Well, if I take 8.3145 joules, I'm going to ignore the rest of the units, just worried about joules. I know that 10 to the third joules are in 1 kilojoule. So here we need 8.3145 times 10 to the negative third, parentheses, 1 over. This is where we need our second temperature, so that's 35 degrees Celsius, which means we're going to take 35 plus 273 and end up with 308 minus 1 over 278. No, 275. Now you have to do is solve for E sub A. And for this one, negative 2.077 equals negative E sub A over 8.3145 times 10 to the negative third multiplied by, and we end up with negative 3.896 times 10 to the negative fourth. And just so you know that this number, this sign in front of E sub A, this, I just double checked. Take that out of there. Okay, that's much better. Okay, now that we've done that, we end up with, and I'm going to have to drag this over here, negative 2.077 is going to equal negative 0.0469 E sub A. And so our activation energy will equal 44 kilojoules. Make sure you can solve for any one of the variables in this equation. Good luck on the test.